Okay, we are going to continue on in module number 8, where we are going to be looking at the second half of the chapter 9 that's assigned here. So you'll notice that there is a handout for chapter 9. There's also an appendix page that we'll be referencing for some problems we already have. But we are going to be going to the second part of this learning plan, and that's going to pertain to the second handout that's here. I already have mine printed out and I have it underneath my camera. So we're going to go underneath right here and we'll start looking at moment of inertia. I'm actually going to minimize that. There we go. So I'm going to zoom in here. And you'll notice at the top here, moment of inertia. You guys have already talked about inertia, for instance, in your physics class, right? And can anybody tell me the concept of inertia, like what does that have to do with? I know it's like one of Newton's laws, but what when you talk about inertia, what do you understand about inertia? Right. So whatever state a body is in, right? It is, we don't want to stay in that state, whether it is still or in a static state, or if it's moving, it wants to continue. And its ability or its want to do that, if you would, even if it's not something that's really alive, has to do with inertia, because if it has mass, that mass wants to continue in whatever state of motion or state of rest that it's in, unless acted on by an external force. Okay. So it's a resistance to changing its state of motion, right? Inertia is a resistance to changing its state of motion. So here we have moment of inertia. Moment of inertia, by definition, it's a cross-sectional area's ability to resist bending, So the higher the value of moment of inertia, the less it's going to flex or bend under load. Okay, so you can imagine, kind of by that definition, that's going to be something that we're going to be interested in, especially when we have beams that are supporting things like well, different types of loads, but frame members, or even if you're in the constructions industry, you know, the framework on a house, bridges. Statics is a class actually, and this particular subject is going to be something that crosses over a lot of different disciplines. Okay, so so moment of inertia has the variable capital I. And a really good example of this that I think you can relate to. Now, I don't have physically a yardstick here, but I think you'll get the idea just based on experience. So here we have, for instance, the cross-sectional area of a yardstick. In the first instance, with the XY axis here, we have it laying down like flat with its wider horizontal. And if I would take that yardstick and I would try to bend it, you know, over that flat area, it's pretty, you can flex it pretty easily, right? Would you agree? Can you kind of imagine that with me? If I take my my yardstick and well, I can kind of look at it this way. In this orientation right here, it would flex really easily, right? With that dimension, this horizontal dimension down. Okay, really easy to flex. But if I just stand it up in this orientation, all right, so that this dimension now is going to be vertical, and I try to take that and try to bend it, you know, like in this, like the same way, I can't do it, right? So so what happens is it becomes more stiff. It becomes more resistant to bending just by taking that very same cross-sectional area and standing it up on its tall dimension. Does that make sense to everybody? Okay. If you go down in your house, in the basement of your house, and you look up, and if you haven't remodeled your basement, you can look up and you can see 2x12s, okay? And those 2x12s are standing up so that that vertical dimension is the tall way, not laying flat. It would be really bad if it was laying flat, because then your floors would want to flex, okay? 2x4s or different types of structures, when you see on buildings, you're going to notice that tall dimension is usually the dimension that's going to be standing upright, supporting things, because it's going to resist bending more. Now, how do we quantify that? And that's what moment of inertia is. It's a way for us to get numbers exactly at that, what we know is going to be true. Okay. So what we want to do is we want to calculate the moment of inertia of the shape that we have here, the cross-sectional area, when it's laying down, and then we're going to calculate it again when it's standing up. Okay, so moment of inertia, capital I, sub x1. All this is saying that we're gonna determine the moment of inertia about the x-axis. Now, when we say about the x-axis, in this case, the x-axis is horizontal. And it means that if I were to apply a load like I did earlier, where I was going like this, it would be a load this way. That means that my load is going to be perpendicular to the axis that I'm looking at, and my base is going to be parallel to that axis then. That's how we know what orientation it's in. So the equation to calculate the moment of inertia of a rectangle is going to be the base times the height cubed divided by 12. Base times height cubed divided by 12. This equation is found in our appendix in the second table. We'll be looking at it a little bit later, but it's going to be the same one we reference here. So as we look at our dimensions on the left-hand side, our 1 inch is going to be our base. Our 0.188 is going to be our height. So this, I just have a number, you know, I measured about an inch wide on my yardstick, and about 3/16 inch thick is going to be the thickness of the material there. I cube that value, and then I divide by 12. So tell me, what is the answer you get here when you do that math? Okay, so I'll fill in what you guys tell me. What do we got? I got a 0.015. I think it's a little bit smaller than that. Make sure you're cubing the 0.188.
5.5.
Point 0.00054. Is that what it is? 1, 2, 3, 4 to the -4, right? Okay, so 0.00054 inches to the fourth. Now, inches to the fourth, it's because we have cubed inches here times inches there. So when we multiply those two together, it's inches to the fourth, and those are always going to be the units to the power of 4 for moment of inertia. Now down here, we're just tipping that yardstick up on end now. And as we know, when we try to bend it in that same orientation, it's going to be stiffer. It's not going to want to bend. It's going to resist bending, okay? More so than in the upper orientation. So we want to quantify that. So this time our base is going to be the 0.188. That's what we see here. And our height this time is going to be the 1. So we're going to cube 1, multiply by 0.188, and divide by 12. And what is this number? 0.0157. Okay. Now, look, they're still pretty small numbers, right? They're not like huge numbers, but you can see that there is a considerable difference between the two. So we already know it's going to bend more easily. It's not going to resist bending as much in the top orientation than it will in the bottom. Okay, so the higher our number for moment of inertia for I is always going to mean that we're going to resist bending more. Okay, more. Now, if we take the bottom number and we divide by the top number, what do we get? So if we take 0.0157 and we divide by 0.00054, what is the number that I get here? So 28 point what? 28.3. So what that means is the bottom orientation is 28.3 times more resistant to bending, or it's 28.3 times stiffer than the orientation on top. So by taking that very same orientation and just by tipping it on its end, it really changes, you know, how it's going to perform. Okay. Yeah.
So the inches to the fourth, is that just an arbitrary number, like arbitrary unit?
No, never. Well, inches to the fourth is just because of how it's calculated. Right. So you'll notice that whatever units we're working in, so in this case, it's inches, it's going to be inches cubed times inches. So it's inches to the fourth. So we will always have moment of inertia to the power of 4 for its units. So it might be in millimeters, it might be inches, but yeah. Mm-hmm. Good. Other questions before we turn the page? Okay. If we look to appendix A2, so in that second handout, as part of this chapter, on page 455, this is our chart or our table for moments of inertia of simple shapes. So you'll notice that we have square, triangle, circle, half circle, and a quarter circle. And in the left-hand column, this is moment of inertia about the x-axis, and that's going to be identified as just the x. So in this case, on the bottom of the part. But the one that we're going to use is going to be, for pretty much everything, is going to be the moment of inertia about the centroidal axis. So it's x sub c. So we find where the centroid is of the part, and we put the x-axis through there, and that's going to be the equation that we see here. Okay, so b times h cubed divided by 12, which is the one that we used just now for that yardstick problem. And then we'll have different versions for the different shapes that are here. So appendix A2, which is the second page in that appendix, that's where we're going to find the moment of inertia information. Okay, A1 was the area stuff for the simple shapes. Okay, and then A2 is going to be the moments of inertia. And that's going to be when we're just dealing with squares, circles, triangles, and such. So as we turn the page, you're going to notice at the top here, this is going to be section 9.8 in our book. It talks about the parallel axis theorem, So the parallel axis theorem, by definition down here, is a theorem that's used when the reference axis does not pass through the centroidal axis of the simple shape. We saw something similar to this in this sense when we did centroids, because when we had our reference axis, if it didn't move through the centroid of the simple shape we were looking at, we would get an x distance, an x1 and a y1, or an x2, y2, for that corresponding shape. Really the same thing's happening here, but now we're dealing with moments of inertia. So it says parallel axis theorem. Let's kind of break this down. So as we see here, this is going to be the moment of inertia about whatever reference axis we're looking at. And so it'll be identified. And in this case, they're just calling it out as reference axis AA, okay? And the line above just means it's kind of like the overall, or it's the total. And it's going to be equal to the moment of inertia about the centroidal axis, okay? And this is what we would get from, for instance, if it's a simple shape, we would get it out of the appendix, out of table 8.2, or if it is a standard structural type of a shape, then we would get it out of the chart that would be corresponding to that. And we'll see some of that later. And then we're going to say plus the area of that simple shape times the distance that centroid is away from this reference axis. Okay, so like in the centroid examples that we did, or the problems that we did, that was the x1 or the y1 distance. Here, this would be a distance in the x or the y similarly. Now, as you can see here, we have to square that distance, okay? Because if we look at units for area are going to be squared. Units for distance are going to be inches, but then because we're squaring it, it's going to be squared. So when we multiply a squared value by a squared value, that becomes to the fourth power. Okay, so then we can add this to moments of inertia, which are to the fourth power. Okay, so make sure when you do this, so a very simple thing that can happen, and it's happened to me too, forgetting to do that square on the distance before you multiply by the area. Or some students will multiply the area and the distance first and then square the entire quantity. So just be careful with that. You only square the distance and then multiply it by the corresponding area. All right. Now, when the axis goes through the centroid, this distance goes to 0, and then we don't have to worry about it. Then your moment of inertia, if the reference axis goes through the centroid of the shape, then these two are equal. Okay, and we'll see some instances of that as well, but we'll always have a drawing and we'll be able to identify when it's appropriate. So parallel axis theorem. If you go home tonight and somebody asks you, what did you study tonight? You're like, bah, it got good. We talked about the parallel axis theorem, and it sounds so smart. And it is. It's not like small stuff, but you're gonna, and then when they ask, well, what is that? You're gonna say, well, that's when we use it when the reference axis doesn't go through the axis of the simple shape. Yeah. So So we're going to practice using that tonight. I don't know if anybody goes home and tells people what you do, but you do smart stuff. You do smart stuff. And this one sounds pretty smart. So, so as we look here, you're going to notice that we have a simple, just kind of a simple body, a simple shape. And over on the right-hand side, I'm just giving the area as 25 inches squared, okay? Then you're going to notice that the moment of inertia about that same shape is going to be 60 inches to the fourth. So instead of calculating those, I'm kind of giving them to you so that we can practice the parallel axis theorem. And what we want to do is we want to determine the moment of inertia about this axis right here. This is the reference axis, okay? And that reference axis is vertical, So when we want to find it about that axis, we're going to say it's going to be equal to the moment of inertia about the centroidal y-axis for this shape. And it's the y-axis for this shape because it has to be parallel to the axis that we're summing around. So since our reference axis is vertical, the axis going through our center has to be vertical, which is the y-axis, okay? And then plus the area of that shape times, now it's distance x, and it's distance x because it's the distance between these two vertical axes. It's a horizontal distance, so it's considered a distance in the x direction. So in this case, it's 10 inches between the two, so that dx would be 10. So this is your base equation. Always show me that in variable form. And then you'll notice that we have the values down below. So the 60 inches to the fourth is that moment of inertia about the centroidal y-axis. So that goes right there. Plus 25 inches squared is our area. And then our dx is 10 inches. Make sure you square the 10 inches first, multiply by the 25 in this case, and then add to the 60. So we would get 2560 inches to the fourth, okay? Now, if the reference axis goes right down the middle here, then this goes to 0, and then those two are equal. It didn't in this case, it was offset, and that's why we had to take the a times the d squared, okay? So only when that reference axis doesn't go through the centroidal axis of your shape. All right, so that's that. Let's look at our first example. Our first example is going to be on page 195 in our handout. And I already redrew the illustration here, and I have the instructions down below. But if you wanted to open up to that page, you certainly may. It says we want to find the moment of inertia of the right triangle right here shown in figure 919A, which is referenced in the book, for the x centroidal axis and for the x reference axis, which is right here. So our reference axis is right here. And that x centroidal axis is right there. So we want to know what is the moment of inertia about that shape, about its centroid of that simple shape, and then what is it in reference to the reference axis here. So for the first one, the centroidal axis, we'll be able to just go to the back of the book, find the corresponding equation in that second column, and we can plug that right in with the numbers we have here. So the moment of inertia about the centroidal axis of its own shape, real easy plug and chug. But once we are then going to be in reference to an axis that is not running through that center, then we have that offset distance with the parallel axis theorem. So we'll be doing both here. So down below, I give you some steps to follow. And the first thing I want you to do is to determine the location of the centroid of that triangle, okay? So right now, you're going to notice that we have the offset distance here. We don't know what that is. We do know that the bottom of this triangle is going to be 4 inches from the reference axis. But we still need to know, for instance, from the bottom of that triangle to the centroid, what that value will be, okay? Does anybody know what kind of the standard equation, if you know it off the top of your head, what this distance right here, this, we'll call this a y bar distance would be? Yeah, it's the height divided by 3, right? I'll actually put it up here. Y bar is going to be equal to the height divided by 3, or 1/3 the height of that triangle. If you're not sure, where can you look? Yeah, there's a table A1 it was the very first table in the appendix, okay? So the very first page here, 454, and it's this table right here, and that Y value When we look at this right triangle, if the height is the overall height here, it's h divided by 3. Okay, h divided by 3. And y bar is right there. And I say it's from, you know, one of the legs, not from the point. If you're going from the point down, it would be 2/3, right? The height, but we're going up from the leg or the base. So you can always confirm it there if you're not exactly sure. I don't expect you to know these off the top of your head. So if we have that, y is equal to h divided by 3, our distance then is going to be equal to 10, right? So it's going to be 10 inches divided by 3, which is going to be 3.333 repeating, right? Inches. We'll do D in a little bit, so you can wait on D. So our Y bar is 3.333 inches. The next step is to determine the area of the triangle. Okay, the area of the triangle. So an area of a triangle, what's my equation for area of a triangle? Base times height divided by 2. But again, if you're like, ooh, I don't remember, or you're just not confident, you can always look to this table A1, the very first table, and the first column here for that triangle is base times height divided by 2. So that's what we're going to put in here. So B times H divided by 2. So our base in this case is 6 inches. Our height is 10 inches. So 6 inches times 10 inches. And we're going to divide that by 2. So it looks like it's 60 inches squared. So our area is going to be 30 inches squared. Now, the next step, number 3, it says determine the distance that the centroidal axis of the shape is from that X reference axis, okay, the DC. So when we look back up here, DC is identified. So from that reference to the centroidal, it's right between here. So we know that our distance from the bottom of our triangle to our centroid is 3 1/3 inches, right? We also know that the distance from the bottom here is 4 inches. So this is going to be 4 inches plus 3.333 repeating inches, right? So if we look down here, this is going to be 7.333 inches. Okay. All right, turning the page. Now, the problem wants us to determine the moment of inertia about the X centroidal axis. Okay, now that means that it's of the actual part. Okay, that's the simple shape. So we're going to go to that table A2 on page 455. Okay, we're going to find the row with the triangle, and we're going to go down the column that says IXC. And it's base times height cubed divided by 36. Base times height cubed divided by 36. So we're going to put base times height cubed divided by 36. We know that our base is 6 inches and our height is 10 inches. So we have to get the base and the height right. The base is always going to be parallel to the axis that we're summing around. We're summing around the X centroidal axis. The 6 inches is parallel to that. Okay. So base is going to be 6 inches and our height is going to be 10 inches. Cube that and divide by 36. So our IXC for this triangle what do we get? Yep, that's what I got. 166.67. And what are the units? Inches to the 4th, exactly. Inches to the 4th. So that's part of our problem, right? That they were asking for. Now, the last part of this is looking at what is the total moment of inertia, but this time about the reference axis, the reference axis. So if we go back to our illustration, our reference axis is right here. It's off the part. It does not go through the centroid of our part, okay? So this means that we are going to have to exercise the parallel axis theorem, okay? If it went right through the axis, we wouldn't worry about this. The centroidal axis, the moment of inertia about the centroidal axis would equal the total, okay? But because it's offset, we now have to add area times the distance squared, okay? Area times the distance squared. So on the back side here, what we want to do is we want to say, all right, this is the moment of inertia about the x centroidal axis, which was what we just calculated, okay? But it's going to be plus the area of that shape times the distance, and we call the distance c, and I'm going to put it in parentheses, and I'm going to square that quantity just to make sure that we don't forget that it's just that distance squared. So now we'll put our values in. So it's going to be 166.67 inches to the fourth plus the area. We just calculated the area. In step number 2, that was 30 inches squared. So this is going to be 30 inches squared times our DC. Our DC was 4 plus 3 1/3, or 7 1/3. 7.333 inches. And we need to square that quantity. So our total moment of inertia you get 779 inches to the fourth, or I think the book says 1780. They go to 3 significant digits. Inches to the fourth. So questions so far, first of all, when and when not to use the parallel axis theorem. Parallel axis theorem is only used when there's a distance. If that axis passes through the centroid, well, then this distance goes to 0. So this goes to 0, okay? So only when it doesn't pass through. So again, it's kind of like the composites where we were calculating those centroids, and it's those x1, y1 distances and such. Okay. All right. So that's a kind of our first little problem. So let's continue on in our handout. Okay. As we look at our next page here, you're going to notice that we have a process. Okay. So our next section looks at what is the process that we're going to use to determine moments of inertia, not about simple shapes, because those aren't all that complicated. They're pretty easy, as we just saw, whether they're going through the center of the axis or not. But now we're going to be looking at composite areas, just like we did for centroids, okay? So the moment of inertia about a composite area has a process that we go through. So first of all, we need to break our shape into whatever simple shapes there are, just like we did for centroids. Then we need to establish a reference axis. Now, depending on the problem, they might be asking, do it about the centroidal axis of the composite. And if you don't know what the center of the centroid of the composite is, then you need to calculate that first. So it's kind of like we're first going to do the centroid, and then we're going to do the moment of inertia. All right. And then, so once you have that axis established, then what you're going to do is you're going to gather the following information about each one of your shapes. We need the area, we need the centroidal moment of inertia, and then we also need the distance that that centroid is from the reference axis, okay? Then we're going to create a little table, okay? And the table is going to be filled with values that pertain to the equations to solve for the total moments of inertia. So I'm going to peek down here first. So this should look familiar to us, the parallel axis theorem in terms of the x-x axis. So whatever the x reference axis is going to be the summation of the moments of inertia about the centroidal x-axis plus the summation of the area times the dy's, okay? And then the other equation is going to be the same, but it's for the y-axis. So now you're going to notice that in our table here, when we want to find our values for our moments of inertia, we're going to need distance d's, whether it's x and y's or just x's or just y's. And then we're going to need a column for the area times whatever corresponding dx or dy that's going to be there. So even though we show just 1, 2, 3, 4, 5, because there could be the potential of x's and y's for both, it ends up being a longer chart in the end. Now, for those who had me for computer programming earlier this fall, right? You guys did these problems. Yeah. So, so although I'm going to ask you to show your work, you can definitely check them with those calculators. Okay. So I do want you to show your work for these. Right. But then you can just kind of prove and just make sure that you have the right answers. Okay. So, so let's kind of use this process to go through our first example. Okay. Now, so our first example isn't an example out of the book. This is one that I created just to kind of show the process that we're going to go through without like terribly complex parts. So what we have here is, if you would, a pretty standard I-beam. I don't know, it's not really an I-beam, but it's an I shape cross section. And what we want to do is we want to calculate the moment of inertia about the x-axis and the x-axis and the y-axis. So right now we have our reference axis, the x and y, right at the centroid of the composite. Okay, so each one of these means that we're getting the total moment of inertia about the centroid of this composite because our reference axis is right there. So this is one of our first steps. We want to identify the reference axis. Now, because it's at the centroid, we don't have to calculate the centroid. If it's not at the centroid, or if the centroid is not identified for you, then you have to do that work first. Okay, then it becomes a little bit longer problem. So in this case, we're starting with the centroid and we have it as our reference axis. So that's why I chose the example to just really kind of start us out by going through the process. Now you'll notice here that we've got a vertical section and we've got 2 horizontal sections on either side. So the procedure says break it into its simplest shapes. Okay, so so the simple shapes that we're going to have here, I'm going to kind of put a dotted line across and across. And you're going to notice that we'll have 3 rectangular shapes. I'm going to do number 1 as the one that's standing up in the middle. Number 2, the upper, and number 3 is going to be the lower. Now, by design, the upper and the lower are evenly distributed from that centroid, and they're also the same size. So they're 1/8 on the top as well. Okay. Now, just like we did for our centroids, we are going to now look at each one of these simple shapes on a separate axis system. So if we go back and we look, we're on step number 3, and we want to gather the following information about each one of our shapes: the area, the centroidal moment of inertia, and the distance of that centroid from the reference axis. Okay. So we can make this, you know, a little bit smaller. It doesn't have to be as big as what we have up there. So this is going to be our, I'm going to show my X and my Y axis. This is going to be my X and my Y. And then I'm going to have sin. And we know this to be 1 inch. We know this to be 8 inches, evenly distributed on that axis. And then this is our centroid, right? So this is going to be centroid 1, and our X and our Y are the reference axes for us. Okay. Now we need to gather the area. So area 1 is basically going to be base times height. And I trust that you guys have a good handle on that. So you can just put 8 inches squared. In my last section, they're like, do we really have to write out base times height? Show the units. I'm like, no, I'll let you have it. Okay. Just make sure it's right. But identify A1 is equal to and just put the final number. With rectangles and such, it's pretty easy. Then we need to find our moment of inertia about the x centroidal axis, and we're going to call this shape number 1. Okay, now recalling, but if you need to look, don't, it's totally fine. But if we look on that A2 table, our equation for the moment of inertia about the x centroidal axis is the base times the height cubed divided by 12. Okay, base times height cubed divided by 12. Now, I'm going to write this little note here. My base is always going to be parallel to the axis you're summing, or you're just to the axis we'll put, okay? Just to the axis. So if our axis is the x-axis here, our base is parallel to the x-axis. Okay, so if you're ever wondering, like, am I the base or the height here? I don't remember. It's always, the base will always be parallel to the axis that you're determining it of. So that means that my base in this case is going to be 1 and my height is going to be h, or my height is going to be 8. So my base is 1 inch and my height is 8 inches, and I have to cube the height. Okay. And then divide by 12. So my IXC1, what do we get for that value? What do you get? Oh, it is. I'm so sorry. It is 6. I was thinking 8 overall. I'm so sorry. It is 6, 6, 6. Thank you. Thank you. 6, 6. So 6 cubed times 1 divided by 12. What do we get? What was that? It should be 6 then. Yes. Thank you, Jack. And did you get 18? Inches to the 4th. Inches to the 4th. So we're going to need that in our chart. We'll need our area. We'll need our moment of inertia about the x centroidal axis. And then we'll also need the area about, or moment of inertia about the y centroidal axis, number 1. And again, that's going to be base times height cubed divided by 12 using the correct dimensions. So my base this time, now this is about the y-axis. The y-axis is vertical. So if you need to, it's always more natural that the base is like sitting down horizontally, right? So since we turn this so that the y is horizontal, then that means our 6 inches is going to be the base in this case. So my base is 6 inches. My height is going to be 1 inch, and we cube the height divided by 12. Okay, so my IYC1, what do we get for that one? 0.5, yep. So it would be 1 cubed is 1 times 6 divided by 12. So 0.5 inches to the 4th. Good. Any questions right now on that? All right. So now we're going to move on to our next shape, and we're going to draw it with relation to the reference axis. Now this one is going to be shape number 2. So it's going to be up on top here. Okay. And since this is 6 and it's evenly distributed at the centroid, that means that this distance right here, half of that distance to underneath that shape number 2 is going to be 3 inches then. Okay. So we need to then draw this shape on the next page. X, our Y. Shape number 2. And we know that the distance underneath here is going to be 3 inches. The height is 1 inch. And then the length here, this is the 8-inch dimension. I was remembering 8 inches across. So our centroid would be right here, right? Our centroid number 2. So our area number 2. Draw this for our reference axis. Our area number 2 is going to be 8 times 1. There's my 8 inches squared. I literally just did this problem like 4 hours ago. And my IXC2, still going to be base times height cubed divided by 12. Remember, my base is parallel to the axis I'm summing around. My x-axis, that means that my base is going to be the 8 inches. And my height then is going to be the 1 inch. And I'm going to cube the 1, multiply by the 8, and divide by 12.
For,
Not right now, not right now.
why? Oh,
So here, what do you get for your moment of inertia about the x-centroidal axis? What was it? Yep. Inches to the 4. Okay. Then our IYC2. Base times height cubed again, divided by 12. Now, because this is the y-axis this time, it's kind of like we're sitting it down this way, different orientation. So your base is going to be parallel to the y-axis. So this time our base is 1 and our height is the 8. And we have to cube the 8 then this time. What do we get for IYC? Number 2.
42.6.
So 42.67 inches to the 4th, right? Inches to the 4th. Now, in the room, Josh asked about, well, what about that 3 inches? Are we doing anything with it? We could right now, or we could wait. I always usually wait until we look at our stuff, but why don't we put it in right now? Okay. Now, remember, when we use the parallel axis theorem, in this case, when the x-axis does not run through the centroid, right? So this would be our x-centroidal axis of our rectangle. We would have then a distance in the y direction for shape number 2, right? So that distance, dy2, is going to be equal to 3 inches plus half of 1, or 3.5 inches, right? Now dx, if we look at our centroid of our shape, it runs through the reference axis. Do you see how dx2 is going to be 0? Because there's no offset. And that's really why we didn't have it earlier for the previous shape. Let's just peek back at number 1. Because the centroid was going right through that reference axis, dy1 is equal to 0, and dx1 is also equal to 0. Because there's no offset from the reference to the centroid in either direction, because it's going right through the centroid of that first shape. Okay. So we'll put them here right now. Since you recognize that, we'll take care of it. And then we have our shape number 3. Shape number 3, okay. We're going to go ahead and we're going to draw our X and Y axis again. Kind of keep it up higher. Okay, here's our X, here's our Y. And then I'll extend this down a little bit. And then we're going to have our shape number 3 down here. C3. Reference axis. We know that this distance is evenly distributed, right? To the bottom of that. With 6 on top, 6 on the bottom for that shape number 1. And then this is 1 inch again. This is 8 inches. So since our dimensions are the exact same as they were for shape number 2, our area number 3 is going to be 8 inches squared. Additionally, our moment of inertia about its centroidal x-axis is going to be the exact same as here. IXC3 is equal to 0.667 inches to the 4th, which is the same as the x centroidal for 2. And then our IYC number 3 is also going to be equal to the same as 2 at 42.67 inches to the 4th. Does everybody see why that is? It's still the base times the height cubed divided by 12 about its individual centroidal axis. Okay, individual centroidal axis. So because they're the same size shape, their area and their moments of inertia will be the same. Okay. Now, if it was rotated in a different orientation, then they wouldn't be. But in this case, they're sitting, you know, horizontally exactly the same except top and bottom. Now, dx and dy for number 3. So the dy distance for 3 is going to be down to the center there. So my dy is going to be equal to 3.5, but it would be a negative 3.5 inches because it's going to be down below the x-axis. And I'm going to put a 3 in back of that. And then dx3, what's that value? 0 again, right? Because if we extend this through, it's going to go right through the centroid. It's not offset horizontally. So dx3 is equal to 0. dy3 is equal to, there we go. Okay, so now what we've gathered is the information that we need to fill in our chart, right? To fill in our chart. So, on the opposite side here, there's one more blank piece of paper. And this is where we're going to create our chart. Okay. So we're going to go across the top. And this one gets a little bit longer just because there's more that we have to fill in. This is going to be our shape. And then we're going to have area. And that's going to be in inches squared. Then we're going to have distance x in inches. Distance y in inches. It's really just grabbing all the variables that we collected. Then we're going to have an a times dx squared. And that's going to be inches to the 4th. I put my units in the top just because that way I don't have to include them in my cell, if you would. A times dy squared, inches to the 4th. And then I'm going to have my IXC, inches to the 4th. And my IYC And that's also inches to the fourth. That's my staple there. And we're gonna have shape 1, 2, and 3. And then this is gonna go across. And then we'll sum some of these. Okay. So I'll let you catch up to the columns. And these are just going to correspond to, and I'll write the equation out in just a second after you get this. So it'll make sense why we chose the headings that we did. Now, just below here, before I start filling this in, I want to kind of show you why we did what we did. So we are looking for the moment of inertia about the x centroidal axis of this part, okay, which was identified in our original problem as going right through that center. So we want to know what is the moment of inertia about the horizontal axis x here and the vertical axis y. Okay, the vertical axis y. So we are going to, moment of inertia about that x axis is equal to the summation of the IXCs plus the summation of the area times the dy squared, okay? Now it's dy with the x, because remember, if it's a horizontal axis, our dy is in this direction, okay? If it's a vertical axis, it's with a dx. And then I'm going to leave a little space because we're going to be putting numbers in there. And my IYY total is going to be equal to the summation of the IYCs plus the summation of the A times the DX squared. Okay. So this is like our end. And that's why I wanted to go back up here. And now we're going to sum a couple of the columns, not all of them, a couple of them. So we're going to sum the IXC. So it's going to be this one right here. And the A times the DY squared, this one right here. Right. And then we're going to sum the A times the Y, or the IYC. And then the A times the DX squared, which is right here. Okay. And we don't need to sum these three. We're just using those to get our calculations. And those were values that we had gathered. So now what you can do is go back into each one of the shapes and fill in the chart. Okay, and then do your sum. So I'm going to give you some time to do that. All right. So you're simply going to go back to, for instance, shape number 1. Here's its area. Here's its moment of inertia about the x centroidal axis, y centroidal axis, and then the dy and the dx. You're going to fill those in. Then you're going to go back to shape number 2, which is on the back side of this piece of paper. And here's shape number 2's information. And then shape number 3. And you're going to fill in the columns, and then you'll have some that you'll have to calculate. You can compare. I want you guys to go back and find your answers, because I know it's tempting to just fill in. I have all the answers figured out. But I want to make sure that you know where they're coming from. So go back and check in each one of the parts to fill in, and then I'll pull mine up and we'll compare in just a second. So you should have your calculators out and calculating the items in the columns, like the a times the dy squared, or the a times the x dx squared, dx squared. Doing the sum of the columns. It's not hard work, but it's, you know, it's taking your time on your calculator and then just making sure they're getting punched in correctly, and then double checking them as well. So you should get for your overall moment of inertia about the x centroidal axis, 215.33 inches to the fourth. And then for the moment of inertia about the y centroidal axis, 85.84 inches to the fourth. Now, thinking back to moment of inertia and its definition, okay? And its definition, and how it says that moment of inertia, it's cross-sectional areas, ability to resist bending, okay? The higher the value, the less it will bend or flex under load, right? So if that's what I was interested in, orientation-wise, which way would I position my I-beam, I-shape? This way or this way? With the X horizontal or with the Y horizontal? And if I look back at my numbers, if I want it to be, if I don't want it to deflect as much, if I don't want it to move as much, which orientation will I want to set it in? Lex. In the X, right. I want it this way, because this way, 215.33 compared to the 85. Now, even though we have, you know, these going up, we have this bridge in the middle that's going to want to flex. That's going to be the bigger deal. Okay. So having it in this orientation, proven by the numbers, has a higher moment of inertia. It is going to resist bending more than in the other orientation. Okay, that's the purpose. So like I said, I know we won't be, we're at the tail end of our semester or our term here, but in strength of materials, you will be using moment of inertia, and you'll be looking at these values and seeing how they affect bending in beams, okay, specifically, and deflection as well. All right, I'm going to stop the recording.